Hi guys, in this video we're going to look at the electronic configuration of ions, and I'll be paying close attention to the electronic configuration of ions formed by some of the transition metals. So on the left of my screen you're going to see a table showing the first 10 elements from the D block series. Right? These are all transition elements or metals. Their atomic number and their electronic configurations, and the electronic configurations for some of the ions they form. I start by first looking at the electronic configuration of a negatively charged ion, as our transition metals will only form cations. So we look at a negatively charged ion, which is oxygen, which forms the oxide anion. So oxygen having an electronic configuration 1s2, 2s2, 2p4 will gain 2 electrons into its outermost shell to give it the electronic configuration which resembles neon. We next go to scandium, where its electronic configuration is 3d1, 4s2. We remember that in an atom where the orbitals are empty, the 3D is slightly higher in energy than the 4s, meaning that electrons will fill into the 4s subshell before filling into the 3D subshell. Once these shells have electrons in them, they revert in terms of their position, that is their energies, where we would say the 3D, which now has some electrons, is lower in energy than the 4s, which will be higher in energy. So that's why the electronic configuration is written with 3D first and 4s after. The significance of mentioning this is that on forming ions, electrons must be removed from the outermost energy levels. That is, electrons will be removed from orbitals furthest away from the nucleus. So we're going to start removing electrons from the 4s before we move into the 3D. So with scandium, with an electronic configuration 3d1, 4s2, for it to form an ion of a 3 plus charge, we're going to remove the 2 electrons from the 4s and then the 1 electron from the 3d. With titanium, we remove the 2 electrons from the 4s and we only remove 1 from the 3d, so that gives us a 3d1 electronic configuration. With vanadium, we're going to remove 2 from the 4s and 1 from the 3d, so that gives us 3d2. We repeat for chromium, and then manganese by removing the electrons from the outermost orbital before moving to the 3d orbital. Let's compare Fe2 plus to Fe3 plus by looking at the electronic configuration of the element iron. So for Fe2 plus, we take the 2 electrons out of the 4s orbital. So this gives us a D6 configuration for Fe2 plus. And for Fe3 plus, we take the 2 electrons from the 4s and 1 from the 3d. Now on my screen, you're also going to see I've taken the opportunity to mention or describe the configuration of the D subshell. So Fe2 plus is partially filled, Fe3 plus is a half-filled D subshell. Let's say, for example, you're asked in a question, why does Fe2 plus readily oxidize to Fe3 plus? You can use electronic configuration to explain your answer. So the Fe2 plus will readily oxidize or lose an electron to form Fe3 plus, and this is because a half-filled D subshell is more stable than a partially filled D subshell. And last but not least, I also look at zinc 2 plus, where zinc 2 plus will lose the 2 electrons from its 4s subshell, and it will have a completely filled D subshell. I'm also going to mention here, and we'll look at it in a later topic, that the S scandium 3 plus and zinc 2 plus, right, their compounds tend to be colorless. Right, so these are any compounds containing these ions. They tend to be colorless, and this is because of a D0 or D10 electronic configuration. Right, so scandium 3 plus, zinc 2 plus tend to be or form colorless compounds. Alright, we'll look at that later on in another topic. For now, this is electronic configuration of some transition metal ions.